So again, looking at the advection dispersive equation, we've talked about retardation, which has to do with absorption. We've talked about how the plumes spread in time and space. But what is this last term here? And this is what we'll call the degradation term. The degradation term is, in this case, using what's called linear degradation, which means that the change in concentration in time is equal to a coefficient times the concentration itself. So this is a linear degradation. And you may recognize this from radioactive decay, for example. Radioactive decay, the amount of decay is proportional to the amount of radiation. So it's always losing a constant fraction of its mass in a given amount of time. It's a very convenient form of degradation because if we double the concentration, the same solution will apply. So in other words, it's a linear. If you double C here, you can double C there, and it still will solve the same equation. So it's whereas, for example, if I had C squared, that would not be a linear equation. If I doubled the concentration, we get a completely different solution. So we're using a very, very special case of a linear absorption here, or linear degradation. And what it gives rise to, the unique solution to this particular differential equation is an exponential, and it has a decay constant times time, okay? Now, what that means is that the decay process doesn't change the geometry of the plume at all. So basically, if we had, and we'll draw space here. So this is the plume moving along, and this will be concentration here. And so we'll take a snapshot, and let's suppose that that was our nice little Gaussian plume in space. And so if we had degradation, what it would say is that the degraded plume is just a linear multiplier of that concentration. At an earlier time, when it may have been that the concentration was quite a bit higher. And similarly, the degraded plume would be a constant multiplier. And so this description of concentration in time and space under the influence of degradation actually gives rise to very, very simple mathematics, where you can add multiple plumes, and you can simply track the shape of the plume and account for the degradation by simply multiplying it by a rate of degradation. Notice that I should have drawn this one a little higher. Why? Because it hasn't been exposed to degradation as long. So this degradation multiplier is getting more and more influential as time goes on. So our undegraded plume might be higher, but our degraded plume might be very, very low. So that's the simplest way to describe degradation. What we've pointed out is we've always used linear descriptors, linear retardation, linear absorption, linear degradation. And that allows us to do the most important thing, which is superposition. We can superimpose solutions because if we double the concentration, it's still a solution. Any new solution added to an old solution is also a solution. So this idea of superposition is one of the key positive outcomes of using a linear degradation and a linear absorption model. Even though those models sacrifice certain flexibility in terms of describing real-world degradation and real-world absorption, in some sense, the added simplicity of being able to write one equation to describe the entire movement is far more important than having the precision afforded by more complex descriptions. Now that is true in many cases. Of course, there are going to be cases where you have to go to nonlinear degradation, nonlinear absorption, and more complex descriptions of transport. But from the idea of capturing the fundamental processes, this solution illustrates the fundamental behaviors of contaminant transport in soils.